Okay, for this type of problem, I like to call this boat on a river. And what you need to know is, I've drawn a little boat. This is the river, and the boat is trying to get across the river. And obviously the boat is moving at a certain speed. So let's say the boat speed, let's make it 3.1 meters per second. And let's say the river, because if the river wasn't moving, the boat would just go straight across and land right there. But the river is going. Let's say the river is going yay big. The arrow is yay big. I like to say that. Anyways, it'd be like 1.2. Let's just make up some numbers, meters per second. So where will the boat end up? If it takes off from right here, and another thing you need to know is how wide the river is. So I'll have to tell you, I have to make that up too. So let's make it be width, we'll say 105 meters. All right, so here's how I work these sorts of things out. So the boat is 3.1 meters per second, and the river is 1.2 meters per second. And essentially, if you imagine, the boat's going to go every second, it's going to go about this far, but the river's going to push it over about that far. And then the next second, it will be that much further across, but the river will have pushed it that much further that way. And you essentially end up, kind of drifting in a diagonal direction. And so I might ask you, how far downstream does it end up? And questions like that. So I might ask you how much time it takes to get across. And in fact, to find out how far downstream, you would actually have to first find out how far across you get. So here's the thing. Here's an observation I made actually later in life. I didn't realize this when I was in college taking physics, but I wish I had. If the boat is traveling at 3.1 meters per second, then every second it's traveling 3.1 meters. What I'm kind of trying to get at is, if you know how fractions work, if the top is equal to the bottom, you can justify flipping it. And the reason that that's important to me is, if you're trying to find the time, you might say, let's see. Yeah, so I tell you that the width of the river is 105 meters. So if I say that let's start with that. If I say that the river is 105 meters across, then we could put it over 1, and then I just wrote that there, but let's ignore it. Let's rewrite this, actually, not ignore it, but rewrite it so that the meters cancel. And what I'm talking about is, if this is equal to that, I can flip it and put the meters at the bottom. This is a very clever trick. Since this is, equal, since 1 second is equal to 3.1 meters, just like you say, sometimes you ask, how far is Reading from here? And somebody might say, they might actually tell you how many miles, but they might also just say, oh, it's 3 hours, That's because 3 hours is equal to however far, because you can basically, they're interchangeable because they are essentially the same thing. So 1 second can go on top. This is like an understood one. These would cancel. Meters divided by meters cancel. And that's what would leave you with seconds. So if we divide this by that, we end up with, seconds is the only thing left. These ones would also cancel each other. So I hope you understand that trick, because it really works well. 105 divided by 3.1 would give you 33.87 seconds. So in other words, that's how long it takes for the boat to get across. And if you think about it, the speed of the boat going this way, even though it's being pushed to the side, it's still the same. If you had the river sit still versus being the river moving, the boat would still end up crossing at the same time. That's just the way it works. So now that we know that the boat's in the water this long, let's start over with this same thing, 33.87 seconds over 1, just like we did this, because we know this is our truth. This was our truth before. We know that the river is that wide, and we just multiplied it times the ratio. This is a ratio of how fast the boat is going. So now we know that the boat is in the water this long, and let's multiply it by the ratio of the river, because we want to know how long this river gets to push the boat, right? Think about it. If the boat's in the water this long, the river gets to push it just as long. So the ratio of the river, if we set it up like this, 1.6 meters over seconds, now the seconds will cancel and we'll be left with meters, which is cool because that's what we're trying to find out, how many meters downstream we end up. So it's the units. You have to understand, it's the units, the fact that the units are canceling this way, that tells us we're doing it right. So 33.87 times 1.2 gives us 40.64, and meters is the unit. That's what we're trying to find. So this is how long it's in the water, and this is how far downstream. So those are two important things that we can find out from doing our math this way. But what makes it so easy is knowing the ratio, multiplying it times whatever truth we start off with. So like I said, we start off with the truth that the river is 105 meters across, and once that gave us this, if we did it right, we know this is also a truth, and we multiply that times the ratio for the river, tells us how far downstream. Next thing we might find out would be the angle, like how far, what's the angle? And in this case, hopefully you can see this. Let me scoot my camera over. If you're going to find the angle, you know, essentially you have a right triangle where you know what the, if this is a right angle, you know the opposite. If this is the angle we're trying to find right here, we know the opposite is 1.2 meters per second, and the adjacent is 3.1 meters per second. So that means tangent of theta is equal to opposite over adjacent, right? If you remember SOHCAHTOA, hopefully you can see this. SOHCAHTOA. So this time we know the opposite and the adjacent, so we're going to use tangent. Tangent of theta equals opposite over adjacent, 3.1 meters per second. And what's kind of interesting here is the meters per second, they're going to cancel each other because anything divided by itself is just annihilated. It's like an understood one. That leaves us with a decimal. So that you should find that interesting because we're trying to get rid of those units for sure. 1.2 divided by 3.1 is, so tangent of theta is equal to 0.387. And what we need to do here is do tangent. It's like dividing by tangent, but on your calculator it's shown as tangent to the -1. That would cancel this because this is essentially like tangent to the 1. So inverse tangent is what they call it. So the inverse tangent of this, because this is going to cancel that and leave us with theta. Theta is equal to whatever inverse tangent is of that. So clear, and we go, see the little tangent -1, if we go second function tangent, so it's tangent to the -1 of that number, 0.387. And we're left with 21.1 degrees. And that sounds about right. If you think about, 3 to 1 or whatever, would give you about, that seems reasonable to me. All right, so I guess I should probably divide this up into neat little regions, keep my work neat. So this was step 1, this was step 2, and then this was step 3. Step 3. Hopefully that makes sense. And you can do, oh, I guess one more thing we could find out is what is the resultant, you know, the boat going this fast and the river going that fast, what is the actual force vector, or not force vector, the speed vector, in this case because we're dealing with meters per second. What is the resultant speed? And you could just do a squared plus b squared equals c squared, or you could do, now that we know what tangent is, I guess you could say number 4, if you did a fourth part, you could say tangent of, not tangent, we want something like sine, because we're trying to get the hypotenuse, and sine and cosine are the only ones that deal with hypotenuse. So let's say sine of 21.1 degrees is equal to opposite, and the opposite is 1.2 meters per second over hypotenuse, and we don't know what hypotenuse is yet, but we can move hypotenuse over there and bring this down there and then solve. Hypotenuse equal to 1.2 meters per second over sine of 21.1. Okay, so 1.2 divided by sine of 21.1, that gives us 3.33 meters per second, which does make sense if you think about the fact that this is 3 and the hypotenuse is going to be bigger than either of these sides. So 3.33 seems to make sense to me. 3.33 meters per second. Voila, that's how you do it. And with that, I think I've covered pretty much everything I could ask you within reason with a boat on the river type problem. If you followed that, good job. And don't forget that you can make up your own boat speed, river speed, and width, and then work it out and see if you can solve that.